In this section, we'll look at correlation, which is a very basic measure of relationship between variables. It's used all the time in data analysis and even in everyday discussion, so you need to have a good understanding of what it means. The example we will use for correlation and regression is based on a data file called tape data. It shows weekly sales of 3M tape over a 2-year period, the price of the tape each week, and whether consumers were exposed to advertising for the tape that week. Download the file and open it on your computer. Our ultimate goal is to forecast sales when the ad campaign is run. We will go through a number of steps in this analysis. First, we will look at correlation coefficients to determine whether the variables are related to each other. Then, we will conduct a regression analysis to understand the effects of price and advertising on sales. Finally, we will use a regression to predict sales. Right now, we will focus on the first step, using correlation. Here's what the data look like. Each row represents 1 week and shows whether an ad was run, what the price was, and the units sold in that week. Note that ad equals 0 means there was no ad that week, and ad equals 1 means an ad was run in that week. To begin, let's ignore the ads and just look at price and sales. Make a scatterplot with price on the x-axis and units sold on the y-axis. This is what you should see. So just eyeballing this, what do you think the relationship is between price and units sold? There's no clear pattern. In fact, it doesn't look like there is any relationship. But to be sure of this, we need to calculate the correlation coefficient, which is a measure of the relationship between two variables. More on this in a moment. To calculate the correlation coefficient in Excel, type the formula shown here, entering the range of the two variables in the parentheses. Like this. Excel will return the value of the correlation coefficient, which in this case is minus 0.065. So now the question is, what does this mean? Let's look at how one interprets the value of the correlation coefficient. The value ranges from -1 to +1, that is, negative to positive. Positive correlation, that is, a positive value of the correlation coefficient, means that variables move in the same direction. As one increases, so does the other. As one decreases, so does the other. The diagram shows a typical scatter plot where the correlation is positive. Negative correlation means that the variables move in the opposite direction. As one increases, the other decreases, and vice versa. The lower diagram shows a typical scatter plot where the correlation is negative. One important limitation of the correlation coefficient is that it is a measure of a straight line relationship between the variables. If the points in the plot lie perfectly along a straight line, the correlation will equal 1.0, which is known as perfect correlation. Here are some other examples of correlation coefficients and the scatter plots that correspond to them. The plot on the left shows perfect positive correlation between x and y. The plot on the right shows zero correlation, even though there is clearly a U-shaped relationship between x and y. So you have to keep in mind that correlation is not a perfect measure of a relationship. It only measures whether the relationship is a linear one, and it does not tell you if there is a nonlinear relationship between the variables, such as the U-shaped relationship shown here. A more typical example of zero correlation is shown in this plot. Zero correlation means that there is no correlation and x and y move independently of each other. This scatter plot looks a lot like the plot we saw earlier with price and units sold. This confirms the correlation of minus 0.0635 that we got, which is close to zero. However, to be sure that it is actually no different from zero, we need to do a statistical test. Strictly speaking, a correlation of minus 0.0635 is small, but not zero. However, because our sample is not very large, the true correlation between sales and price might really be zero, and we are only seeing the correlation of minus 0.0635 because of the small sample, that is, due to sampling error. The purpose of a statistical test, therefore, is to factor in the effect of the sample size and see if sampling error can be eliminated as the reason for the result. Here's how we test whether the true correlation is significantly different from zero. We set up the null and alternative hypotheses as follows. Here, we'll use rho to represent the true correlation between the variables, that is the correlation in the population, that is different from R, which is the correlation in the sample. H0 is that rho equals 0. The alternative hypothesis, HA, is that rho does not equal 0. The test statistic equals R, the sample correlation, times the square root of n minus 2 over 1 minus R squared. If you plug in R equal 0.065 and n equals 135, you get a test statistic of 0.751. We could look up a critical value to compare this to, but it is easier to look up the p-value directly. For this test, we can make use of a p-value calculator found at this link. If you plug in the values of R and N, you get a p-value of 0.45, which is obviously greater than our alpha of 0.05. So what do we conclude? Pause the video for a minute so you can think about this. Hopefully you got the correct answer that we cannot reject the null hypothesis. Remember, the decision rule is if the p-value is greater than alpha, you cannot reject the null hypothesis. Therefore, the correlation is indeed 0. This confirms what we suspected all along, but it's nice to have it confirmed statistically. The last comment about correlation is that while it only looks at two variables at a time, in Excel you can calculate as many correlation coefficients as you like at one time. Excel will put all the different coefficients in a correlation matrix. So let's take a minute to figure out how to read this matrix. This is what a correlation matrix looks like. Even though you don't need to do this now, if you want to see the matrix for your data, use the Data Analysis add-in in Excel and click on Correlation. The variables are listed in the rows and again in the columns. In each cell, you'll see the correlation between the row and column variables for that cell. For example, the correlation between add and units sold is shown in the first column and third row and is 0.6927. The correlation between price and units sold, column 2 and row 3, is minus 0.065, as we've seen before. Lastly, the correlation in the diagonal cells is always equal to 1, because those cells show the correlation between row and column variables, and these are the same variable. So the correlation of a variable with itself is always equal to 1. In the next module, we'll look at regression and see how we can estimate the effects of the independent variable x on the dependent variable y. Finally, we will use the regression for predicting the value of y for a given value of x.